Hello everyone. The title of this video is Use the Properties of Logarithms. All the exercises I'm going to be doing in this video are taken directly from a free online textbook at openstacks.org, and I'm in the Intermediate Algebra 2nd edition text. I'm in section 10.4 titled Use the Properties of Logarithms, and I'm working under the heading of the same title. I'm only going to be working on the even numbered exercises in this video. Alright, these are the ones that don't have a link to the solutions, right, like the odd numbered ones do. So 218, 220, 222, all the way down until, it's going to be a long one, 276. Alright, so a lot of exercises here, all the even numbered ones. I will also have timestamps for when each of these examples is starting in the video. I'm going to have them in the timestamps in the description below. So example 1's timestamp is for when number 218 starts. Example 2's timestamp will be for when number 220 starts, and so on. Alright, I also request that whenever I start a new question or a new part of a question, that you pause the video and try to work it out yourself first before watching me doing it and comparing. Because if you're just watching me do these things and not practicing yourself, well, chances are you're not going to learn all that much. Alright, so my first question is number 218, parts A and B, and I have those written out on paper. Alright, so example 1, exercise 218. And in this first group of exercises, we're asked to use the properties of logarithms to evaluate. And I will slowly reveal the properties of logarithms as they're needed. All right. So for this first page, all right, we're going to need the following properties. All right, so I've got a page here where I'm going to start listing off the properties of logarithms that we will need. All right, so the first one is that the logarithm base b, right, where b is some positive number, I'll write that off to the side, of 1, right, where 1 is the argument, 1 is the input of the log, this will always be 0. And again, b is a positive number. Right. And remember, that's because, if you, and I'm going to be doing this a lot, I'm going to be changing back and forth between logarithmic form and exponential form. Remember this property of exponents, remember b to the 0 power, or if you take a non-zero number, a positive number, and raise it to the 0 power, you get 1. Right? And this was the exponential form of this same statement. Alright, then another property that'll be necessary to help us on this first page. Again, hopefully it's obvious, remembering that logarithms are just equal to exponents, right? The exponent you need to raise the base to get the expression inside the log. The logarithm, base b, where again b is a positive number, of just b is 1. Right? If the input is the same as the base, then the logarithm is 1. And again, if you change this to exponential form, it'll be obvious, right, why this is true. Since if you take b to the first power, right, that's equal to expression inside the log that's equal to b. Right, another property, right, which they'll call one of the inverse properties, but It's another property we're going to need for this page. The logarithm base b of b to the nth power. All right, so here, so instead of having b to the first inside, we have b to, some power n. This is just n. And again, it's very obvious, hopefully it's obvious, to see why this is true when you change it to exponential form. Right? B to the nth power is equal to the expression inside, b to the nth power. That is obviously a true statement. Right. And then the other property we'll need for this first page, right, is if I take a base, right, base b, and raise it to a logarithm base b. Right? So b raised to the log base b of, I don't know, x, why not? Right? Where x is some positive number. Right? Remember, you can only take logarithms of positive numbers. B raised to the log base b of x is just x. And again, this should be obvious if you change it to exponential form. Right? If you change, this is an exponential form. Right? If you change it to logarithmic form, it should be obvious, right? You have the log with base b, log base b of the number on the other side of x, is equal to the exponent on that base, and the exponent on that base is the log base b of x. I mean, this is clearly a true statement. Both sides are the same. Right? The first statement's in exponential form, the next one's in logarithmic form, but they are saying the same thing. Right. So, back to here. Right. Number 1, part A. The log base 4 of 1 is 0. Right? And again, if you want to change things to exponential form, or you should be able to go back and forth, right, between logarithmic form and exponential form. But hopefully this is obvious, right? If I change it to the equivalent exponential form, maybe it'll be more obvious. 4 to the 0 power equals 1. So that's definitely true. All right, a little check next to that. So the log base 4 of 1 is 0. Part B, what's the log base 8 of 8? So remember, this is just what power do I need to raise 8 to get 8? Well, that would be the first power. All right, so the log base 8 of 8 is 1. And again, you can say this statement here is equivalent to saying that 8 to the first power equals 8, which is definitely true. All right. Great. All right, question 2. Exercise 220 from the text. Part A. All right, so here I have 3, a base of 3, raised to a logarithm power. Right? And it's a log base 3. Right? So 3 raised to the log base 3 of 6, right, should just be 6. Right? You saw that was property 4 I wrote up, right up here. If you take a number, raise it to a log with that same base, log with that same number of x, of some input for the log, that's what you're going to get back. And again, if you want to double check this, right, change to log form. Right, this is an exponential form right now. Change to logarithmic form. Well, the base is 3, so if I change it to log form, we'll have log base 3 of the number on the other side, right, the log base 3 of 6, equals the exponent on that base, which was the log base 3 of 6. Well, gee, that is definitely true, right? Those are both the same. Right? So the answer here is, 6, right? 6. Okay. And then part B is the same concept, but this is in logarithmic form right now. What's the log base 2 of a power of 2? Well, it's just that power. Right? It's just going to be 7. The log base 2 of 2 to the 7th power is just 7. Right? Because again, remember what a logarithm is. It's an exponent. This is 2 to what power is 2 to the 7th power? Well, it's clearly the 7th power, right? So the answer here is 7. And once again, if you want to check this out, right, test it or check it, change to the equivalent exponential form, and we'll see that we have 2 to the 7th power equals the expression inside 2 to the 7th power. Hey, that's definitely true. Right. So 7 is correct. Great. And I'm going to be using these inverse properties, right, properties 3 and 4 here. I'm going to be using these for the next several problems. Right. Right, so question 3, number 222 from the text, part A. We have 8 raised to the log base 8 of 7. So you can almost think of these as undoing one another, and you're left with 7, and it's that simple. All right, as long as you have a base raised to the log with that same base of some number, right, some positive number, that's what you're going to end up with. And again, a quick check on this. Take this thing that's in exponential form, right, you have a base to a power, change it to log form, right, change it to logarithmic form, and you'll definitely see that this is the correct result. Because this in log form would be the log base 8 of the number on the other side of 7 equals the exponent on that base of 8, which was also the log base 8 of 7. Definitely the same thing, definitely true. So 7 is the correct result here. Part B, another one where I'm using one of those inverse properties. The log base 6 of a power of 6. You're just going to end up with that power, just negative 2. Right? The log base 6 of 6 to the negative 2 is negative 2. And once again, this is in logarithmic form. If I change to the equivalent exponential form, which I'm not going to do after number 3 here, you should be able to check these on your own. 6 to the negative 2 power, equals the expression inside, 6 to the negative 2, which is actually totally true, right? Both sides are the same. So negative 2 is the correct result there. Wonderful. All right. Question 4, I'm using the same properties. Part A, remember 10 raised to the log base 10. Remember, when there's no base in this text, it's base 10, the common logarithm. So this is 10 raised to the log base 10 of some positive number, right? The square root of 5. So this is just going to be the square root of 5. Right? And again, I leave it to you to change this to logarithmic form and see that this is indeed the correct result. Right? And this was no different than part A of number 3. Right? Where you have a number raised to a log with that base. Right? And then part B, we have the log. Remember, this is base 10. Remember, you could put a little 10 here, and that would be the correct. That would still be the same. Log base 10 of 10 to the negative 2 of a power of 10. Well, you're just left with that power. Right? This is negative 2. Okay. And using the third property of logs I wrote up. And again, I leave it to you to change this to exponential form, and you'll definitely see that negative 2 was the correct result. Wonderful. All right, now I'm still using this these same two properties. And I'll keep referring back. I'm still using this third property and fourth property on the next page. But this time we have base E. Right? Remember that E was 2.718 right? And so on. But E was that natural base. Right? It's about 2.7. And if you recall also, remember that when you see this ln symbol, that was the natural logarithm. This is the same thing as log base E, right? But then very often though they don't write log base E, they write ln, right? Natural logarithm natural. So number 5 part A is really no different than number 4 part A or number 3 part A that we saw. We have base E raised to the log base E of 4. So this is just going to end up being 4. And if you were to change this to logarithmic form, you would see natural log of 4 equals natural log of 4. That's correct. So 4 is the correct result here. And then for part B, the other way around, right? I'm taking the log of a power of E. It's the log base E, right? Natural log of E to the 2, right? Of a power of E. You're just left with that power. This is just 2. Right? And once again, easy check. Change this to exponential form, and you'd have E to the 2 equals E to the 2, right? And that's definitely true. So 2 is the correct result here. Alright, fantastic. Now, we're going to get into a chunk of exercises where we're asked to use something called the product property of logarithms, which I will write up on that property sheet that I started. Alright, so number 5, this is called the product property. I'm just going to write the word product here. Alright, so this states the following. The logarithm, base b, right, some positive base, of a product. So say m times n. Right, so I have a product inside the logarithm. This can be split up, and it can be rewritten, re-expressed as a sum of logarithms. And in fact, it's the sum of the log of each vector. So the log of m times n is going to be equivalent to the log base b of the first factor, m, plus the log base b of the next factor, n. Right? And of course, m and n are positive numbers. Remember, you can only take logarithms of positive numbers and get real outputs, real number outputs. And it really doesn't matter how many factors a product has. If this was m times n times p, then you would just split it up to the sum of each of the log of each factor, log of m plus the log of n plus the log of p. Right? You can extend this. Okay, and this has something to do with the fact that when you multiply two things with the same base, you add their exponents. Right? And in fact, let me show you that right now. Right, if I were to change this statement here to, it's in logarithmic form right now. If I were to change it to exponential form, we'd have b raised to this side, right? B raised to this log base b of m plus log base b of n power equals the number inside, m times n. And let's see if this ends up being true. And again, remember, when do you add exponents? You add exponents when you multiply things with the same base. So this expression on the left here is the same as b to the log base b of m times b raised to the log base b of n, right? If I multiply these two, you'd add the powers. And on the other side, I still have m times n. And then from property 3, or 4, sorry, b to the log base b of m, this is just m, times, and then b to the log base b of n, this is just n. And we get m times n equals m times n. That is true, right? So this property does hold true. If you can check that with exponential form as I just did. All right, and for the next properties, I'm going to stop checking. All right, I'll just write them out and ask you to trust me that they are true. All right, I'll leave them to you to check to see if they're true. But the log of a product is the sum of logarithms, right? The log of each factor added up. And we'll also go the other way. If you see the sum of two logarithms with the same base, you can put them together as a single log of a product. All right, so it goes in both directions, and we'll be using both directions at some point. All right, so I'll leave the product property up. Keep referring back to it. Yeah, and so on the next page, we're asked, the next chunk of exercises, we're asked to use the product property of logarithms to write each logarithm as a sum of logarithms. All right, so example 6, exercise 228 from the text. I have the log base 4 of 6 times x, right? That is definitely a product, right? Multiplication, right? 6 times x. There's a factor of 6 and a factor of x. So I should be able to, by using this product property, split it up to the log base 4 of the first product, the first factor, 6, plus the log base 4 of the next factor, which is x. All right, and these should be the same. Now, I'll tell you right now, the log base 4 of 6, 6 is not a nice power of 4. It is 4 to some power, but it's not a nice power of 4. So I'm going to leave this way. All right, so I'm going to circle this. Now you got to also pay attention to the domain of the problem, right? Remember, whenever there are variables involved, you should be thinking about what you're allowed to plug in. Right? Off to the side here, I'm going to say, x has to be some positive number in order for this to actually work. Because if x were negative, we'd be taking the log of a negative, which is not real. Or if x were 0, we'd be taking the log of 0, which is not defined. Same thing over here, right? So x needs to be a positive number in order for this to actually be a true statement. Now you could also do this, if you want to extend it further. The log base 4 of 6, if you were to write 6 as 2 times 3, right, that's a product. And then we have plus the log base 4 of x. And I have another product, so I can use, there's another product in here. So I can use the product property, right, and say this is the log base 4 of 2 plus the log base 4 of 3, and then you still have this other log that we added plus the log base 4 of x, right? And this is equally valid. And then 2, remember 2 is actually 4 to the half power, right? It's the square root of 4. Remember, square roots, cube roots, roots are actually fraction powers. So the log base 4 of 2 is 1/2. So that's a half plus, now the 3 is not nice. 3 is not a nice power of 4 that I can think of. 3 is 4 to some power, but I don't know exactly what it is. So I'm going to leave that as the log base 4 of 3, and then plus the log base 4 of x. All right, and this is equally valid. All right, both of these expressions that I have in boxes here, right, the log base 4 of 6 plus the log base 4 of x, and 1/2 plus the log base 4 of 3 plus the log base 4 of x, both of these are equal to the original for positive values of x. And let's check this. All right, now here's how I'm going to check. I'm going to use a calculator. All right, I have a TI-84 Plus simulator. Pull that up. And I'm just going to replace x with some number. All right, just replace x with a positive number. How about positive 3? Why not? So first I'm going to enter, now you got to hit the math button to get logs of different bases in here. Log base 4 of, 6 times 3. Let's replace x with 3 and see what happens. Alright, so that's the log base 4 of 18, right? So that's 2.084962501, right? So 4 raised to this power would give me 18, right? 6 times 3. And you could check that, take 4 to that power, and you'll get 18. Alright, well now let me replace x with 3 in our other expressions and see if we get the same result. And we should, right? If that property truly holds, these two expressions I have in the boxes should end up giving me the same thing. So the red, let's put the one in the red box, right? So that's the log base 4. Right, that's the log base 4 of 6, and then we'll go plus the log base 4 of x, but I'm replacing x with 3, right? Plus the log base 4 of 3. And you see I get the exact same number. So that is, and you could do this for any positive value of x, and it should work. All right, now let's try this other one, this last expression here, after I wrote 6 is 2 times 3 and used the product rule again, and then said the log base 4 of 2 is a half, right? Let's take, 0.5, right, 1/2, plus the log base 4 of 3. Right, the log base 4 of 3. And then plus the log base 4 of 3 again, right? I'm replacing x with 3 this time, right? Plus the log base 4 of 3 again, right? Replacing x with 3, and look at this, same exact value. All right, and as I've said, this is a way to check, a way to test to see if you did good, Replace the variables with something that's allowed and see if your final expressions have the same value as the original. And these do when x, when x equals 3 here. Right. But once again, you can replace x with any positive number, and the value of this first expression should be the same as the value of these expressions I have in the boxes. Okay. All right, so I'm just gonna, whenever I see the log of a number, if it's not a nice power of that base, I'm just going to leave it, right? We don't have to do the changing 6 to 2 times 3 and all that, right? So I'm just going to use the product property one time, and then if I have a nice power of the base inside the log, I'll change it. All right, so number 7. We have the log base 2 of a product. Now this time there are 3 factors, but like I said on the page with the properties, you can extend the product property and include every factor, right? Write it as a sum of the log of each factor. So I have 32 times x times y, right? 3 factors. So using the product property, I can express this as the log base 2 of the first factor is 32 plus the log base 2 of the next factor, which is x, plus the log base 2 again of the third factor, which is y. Right? Now 32 is a nice power of 2, right? 32 is 2 to the 5th power. So the log base 2 of 32 is 5. Right, so I'll simplify that. That's a nice one. So we end up with 5 plus the log base 2 of x plus the log base 2 of y. And there you go. And of course, x and y must be positive, right? Because you can't take logs of negative numbers or logs of 0 and get real number outputs that we want. Alright, so that's it right there. Right, 5 plus the log base 2 of x plus the log base 2 of y. And if you wish to check, test it out, just replace x and y with some positive number. Do it here and here, and here and here. So say replace x with 5 and y with 7, whatever you want, as long as they're positive numbers. And see, use a calculator or something, see if that value of the original expression is the same as the value of this final expression. And it should be for any positive value of x and y, but I leave it to you to check. Right? I'll leave it to you to test that one out. Alright, I got one more here where we're asked to use the product property. So example 8, exercise 232. So once again, I have a product inside the logarithm, right? A product as an argument of the log. This is log, now remember this is base 10, right? Log base 10 of 100x, 100 times x, a product. So I should be able to split this up. This is the log base 10, or just log, of the first factor, which is 100, plus the log base 10, or just log, of the second factor, which is x. And then we can simplify. The log of 100 is nice. 100 is a nice power of 10, right? 100 is 10 to the second power. So the log of 100 is 2. Right, so this is 2 plus the log base 10 of x. Great. And this is only going to work out, if x is a positive number, right? X has to be positive. And that's how you're going to test it, right? Check it out. Replace x with any positive number you want and see if the value of the original expression is the same as the value of this expression here, right? 2 plus the log of x. Wonderful. All right, so now the next set of exercises have us, introduce us to a new property. We're going to be asked to use what's called the quotient property of logarithms. Right, so I'll add that to my list of properties. All right, so let's call this 6. Right, property 6, the quotient property. All right, so this, or the fraction property. So this is where I have the log base b of a fraction, m divided by n. Right, so obviously n can't be 0, and these better be positive in order for the right side to work. But yeah, so the log of a fraction, right, if the expression inside the log is a fraction, single numerator, single denominator, then you can express it as a difference of logs, a subtraction. It's equal to the log base b of the numerator, right, m, the numerator, minus the log base b of n, right? The denominator, but minus instead of plus. Right? So yeah, so if you see a fraction inside a logarithm, you can split it up, make it the difference of two logs. And once again, this has to do with the property that, that property of exponents, that when you divide two expressions with the same base, you subtract their powers. And I leave it to you to check. Change this to exponential form and see that you'd get m over n equals m over n. Right? This is going to be true. And once again, m and n need to be positive numbers in order for us to be able to take logs of them. Alright, so I'll keep this up for at least the first of these exercises, right, the quotient property. So in the next set of exercises, we're asked to use the quotient property of logs, or the fraction property, to write each logarithm as a sum or a difference of logarithms, and of course simplify if we can. Right? If we have some nice powers of the base inside the logarithm, you should be able to simplify. Alright, so here number 9, exercise 234 from the text. We have the log base 3 of 3/8. Right. So you see that's a simple fraction, a quotient inside the logarithm. If you see that, then you should be able to use this quotient property to rewrite it. This is equal to the log base 3 of the numerator of this fraction, which is 3, minus the log base 3 of the denominator of this fraction, right, of 8. And this is an easy one, right? 3 is a power of 3. 3 is, 3 to the first power. So the log base 3 of 3 is 1. Now 8, 8 is not a nice power of 3. It's 2 times 2 is 2 to the third power, right? That's not a power of 3, it's a power of 2. So, I mean, you could raise 3 to some power and get 8. It's just not a nice power, like a whole number or a fraction. So I'm going to leave this one the way it is. Right? And there we go. Right? So the log base 3 of 3/8 is equivalent to 1 minus the log base 3 of 8. And I'll check that with my calculator. Right? Why not? Just at least for this first one. Right? So the original expression, right, is the log base 3 of 3/8. Alright, so that's negative 0.89278926007. So 3 raised to this negative power here should give you 3/8, and you can check that. Alright, and let's test it. 3 raised to that power, right, the previous answer should be 3/8, which as a decimal is 0.375. Right, so that's 3/8. That's good. All right, let me actually clear that result. All right. Now we said this log base 3 of 3/8 should be equal to this, right, in my box here. 1 minus the log base 3 of 8. Let's see. And indeed it is, right? Negative 0.89278926007, blah, 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 again. All right, so they are indeed the same value. So we did a good job in using the quotient property. Wonderful. Next question, same thing. Right. So again, I look inside this logarithm. Right. There is a fraction in there, a single fraction. So I should, be able to use the quotient property to rewrite this as some equivalent statement, some equivalent expression. So remember, this will be equal to the log base 4 of the numerator of this fraction, 16, minus the log base 4 of the denominator of this fraction, y. And 16 is a nice power of 4, right? 16 is 4 to the second power. So the log base 4 of 16 is 2. Right, so this ends up being equal to 2 minus the log base 4 of y. Right, and of course, y needs to be a positive number. Right? You can only take logarithms of positive numbers. And there we go. That's as simple as that's getting. And once again, if you want to test it out, just replace y with any positive number. 1, 2, a million, pi, square root of 3, whatever you want. And you can go to a calculator or whatever and check and see if the original expression has the same value as this final expression. And they should, for any positive value of y if you did things correctly. Great, so let's keep going with this. It's continuing to use the quotient property. So once again in number 11, I'm seeing the log of a single fraction. Once again, I see a fraction inside the logarithm. So I should be able to split it up. Right? This will be equivalent to the log base, remember this is base 10. Right? When there's no base, it's base 10, the common log. The log of the numerator, x, minus the log of the denominator, 10. And the log of 10 is 1, right? 10 is 10 to the first power. So we have the log base 10 of x minus 1. And of course, one more time here, x needs to be a positive number, just writing that off to the side. And that's how you can test it. Right? Just replace x with any positive number, and you will see that these expressions are equivalent. Great. And example 12. Another fraction, right? We have a logarithm, natural log, right? Remember, this is log base e of a single fraction. So I should be able to use the quotient property to split this up. Take the natural log, right, the log base e of the numerator, right, of e to the third power. And since this is a nice power of e, this should simplify easily. Minus, and then the natural log, right, the log base e of the denominator, 3. This is simple enough, right? E to the third is just e to the 3, right? So the natural log of e to the third is 3. Right, so this is equal to 3 minus the natural log of 3. And again, you can punch these in. Now there's no variables here. You can just punch that in your calculator as it is, punch this in your calculator as it looks. Right, you should see an ln button in most calculators, natural log button. And they will be, I promise you, equivalent values. Alright, so on the next set of exercises, we're asked to use just one final property. Right, one final property of logarithms called the power property. So this will be 7. The power property. So this is the log, base b of m to the p power. Right. So the log base b of a single expression to a single power. Right. You got to be careful with this one. Everything inside that expression has to be raised to a single power in order for this to work. This is equal to, well, you can kind of think of pulling this power outside. P times the log base b of m to the first power, or just m. Right, so again, you think of this as pulling the p outside and making it, a product. P times the log base b of m. But again, this expression has to be all raised to a single power in order for this to be pulled out like that. All right, and this actually comes from a property of exponents, that power to a power rule. Right? When you raise a number to a power and then that number again to another power, you multiply the powers. And again, I leave it to you. You can change this to exponential form and show that you'd get m to the p equals m to the p. All right, promise you. Great. So let's use this. So I'll keep it up top for at least the first example. So on the next page, we're asked to, next set of exercises, we're asked to use the power property of logarithms to expand each and then simplify, if possible. All right, so 13 here we have log, the log base 3 of a power, and I'll say a power, right? Because the entire expression is raised to a single power, a power. Right? So then I can apply this power property. So this should be equivalent to, pull the power out. It's 2 times the log base 3 of just x to the first now, or just the base x. Now again, in order for this to be true, right, over here we have the log base 3 of x. X needs to be a positive number yet again. All right, and then I'll box that. Let's put this in a box. All right, and let's test it out. All right, let's test it out. You know what? I'm gonna pick a power. I'm gonna pick x to be some power of 3. How about 9 or something? Right? So I'm gonna do this without the calculator right now. I'm gonna let x be 9, right? Some positive number. So over here we'd have the log base 3 of 9 squared, right? That's the log base 3 of 81, which is 4, right? 81 is 3 to the 4th power. So the left side would be 4, and the right side would be 2 times the log base 3 of 9. Well, the log base 3 of 9 is 3 squared, so this is 2. This is 2 times 2, which is 4, and we get the same thing. Great. But that it should work. These should be equal no matter what positive number you plug in. Right, here I tested 9, but you can plug in 1, 2, 3, a million, 1.5, pi, right? And these two expressions will be equivalent. Great. All right. Next one. All right, so now, again, we have a log. Now this is log base 10 of a power. Right? Some expression raised to a single power, a power. So I can apply that power property, right, and just pull the power out front, -2 times, and then the log of x, the log base 10 of x. And once again, because of this log of x here, x needs to be a positive number. But there we go. And I'll leave this one for you to check, right? Just replace x with any positive number in both these expressions, and you'll get the same value. Great. Right. Now the next one, you have to remember radicals roots are powers. Right? Remember that the square root of x is the same thing as x to the 1/2 power. Right? Cube root of x, right? The nth root, right? The nth root of x was the same thing as x to the 1/n power. So you just have to recall that stuff, right, for some of these problems. So the log base 4 of the square root of x is the same thing as the log base 4 of x to the 1/2 power. And there, now I have a power inside the logarithm. And again, it's a power, right? The entire expression is raised to a single power. So I can apply this power property now, pull that half out front. This is 1/2 times the log base 4 of just x now, right? The power got pulled out. And there you go. And once again, x would have to be a positive number. Write that off to the side here. And you can test it out. Replace x with any positive number in both the original and the final expression, and they should give you the same result. But I leave that to you to test out. All right. Number 16. There is a power in here. I have the log base e, right, natural log, of x to a power. This is a power. Right, and the power can be any number, right? Here, power can be a half or square root of 3, rational, irrational, any real number. So I have everything in here is raised to a single power. So I can apply that power property. Just pull the square root of 3 out. This is the square root of 3 times the natural log of x. And once again, x must be a positive number for us to continue working with this. Right? There you go, square root of 3 pulled out times the natural log or the log base e of x. And once again, you can test it out with a calculator. Just replace x with any positive number, and the value of the original expression should be the same as the value of this last expression. Wonderful. Alright, so now in this next chunk, now we have all the properties of logarithms at our disposal. Right, these are all the properties of logarithms that we're using in this video. Alright, so please get to knowing them well. Especially these last three. Alright, because what we're asked to do in the next group of exercises is use the properties of logarithms to expand the logarithm. And then, of course, simplify wherever possible. What we're going to be doing is using the product property, quotient property, and power property to expand a logarithm. Going from left to right in these properties is called expanding. And going from right to left is called condensing. All right. Maybe I'll write that here. So going left to right with the properties is expanding. Going the other way, right, let's use this color. Going this way with the properties, right to left, is going to be called condensing. Right, condense. Right. Sorry, that's tiny. Condense, expand. So yeah, if you have the log of a product and you write it as a sum of logs, that's expanding. If you see the sum of two logs with the same base and make it a single log, right, you go from 2 logs to 1 log, that's condensing. For the quotient property, you see the log of a fraction and you write it as the difference of 2 logs, that's expanding, right? You go from 1 log to 2 logs, expand. The other way around is if you see the difference of 2 logs with the same base, you can write it as a single log of a fraction. That's 2 logs becoming 1 log. That's condensing. And then for the power property, you see the log of an expression to a single power. you pull that power out, right, you kind of lengthen the expression, right? You turn it from one factor into two factors. P times the log base p of n, that's expanding. Going the other way around, if you see a number times a logarithm, you see a number p times a logarithm, and you put that number inside as the power, you've turned a two-factor expression into a one-factor expression. So that'd be called condensing. But we're going to be going in both directions. Alright, so for the next set of exercises, we're asked to expand. Use the properties of logarithms to expand the logarithm. And then, of course, again, simplify wherever possible. Alright, so expanding is just simply do this. You're going to use the product, quotient, and power properties until you can't use them anymore. Until they don't apply anymore, right? Until you can't use them anymore. So this is how we're going to expand logarithms. All right, so in these exercises, we'll be starting with a single logarithm, one term, and we're going to break it, expand it, write it as more than one term. All right, so first you gotta look inside the logarithm and ask yourself, is this a product? Is it a quotient, a fraction, or is it a power? Now again, the confusing thing is I see powers here, but it's not a single power, right? This is not a power. All right, not a power. So I can't use the power property here. What I do see, however, though, is a product. Right? This is a product with three factors: 4 times x to the sixth times y to the fourth. All right. So I'm going to use the product property first. So this is the log base 5 of the first factor, 4, plus the log base 5 of the next factor, which is x to the sixth, plus the log base 5 of the third factor, which is y to the fourth. Okay, so I've applied the product property, and then you keep looking inside the logarithms. Now, when you have just a number inside, unless that number is a nice power of 5, we can stop simplifying this. Now you could think of 4 as 2 squared and use the power property and pull 2 out, but I'm going to leave it this way. Okay, log base 5 of a number, that number is not a power of 5, not a nice power of 5 anyway. So I'm going to leave this one the way it is. But then I look at this next log. The argument is x to the sixth. Everything in here is raised to a single power. So this is a power. A power. Right? So I can apply the power property to this rule, this log. Same thing for this last log here. We have the log base 5 of y to the fourth. All the expression in here is raised to a single power. It's a power. So now I'm going to apply the power property, and we get the log base 5 of 4 plus, then applying the power property to the second log, right? Just pull the 6 out front. 6 times the log base 5 of x. Right? The power came out front. Plus, and then again I'm applying the power property. 4 comes out front. 4 times the log base 5 of just y. And then you look inside these logs. X is not a product, it's not a fraction, and it's not raised to, it's raised to the first power, but it's not raised to an interesting power. Same thing with just y. Y is not a product, it is not a fraction, and it is not a power other than 1. Right? So we're done. This is it. Right? Now again, you could go further by changing 4 into 2 squared and pulling the 2 out, but I'm not going to do that with numbers, right? I'm really only going to focus on the variable expressions. Right? So there we go. And again, because you have just x in this log, just y in that log, in order for these to actually be equal, x and y both must be positive numbers. Right? X and y have to be positive numbers in order for these two to actually be equal. And I leave it to you to check. Replace x and y with any positive numbers you want, and you'll see that the value of the original expression is the same as the value of this final expression. And again, I leave it to you to test that out. Okay. Alright, number 18, same thing. We're asked to expand the logarithm. So you just keep looking inside the logs and ask yourself, do you have a product? Do you have a fraction, a quotient, or a power, right? Everything raised to a single power. So once again here I have a product inside. And I don't know, I have a personal preference with these logarithms. I don't like seeing roots inside them, radicals. So I'm going to rewrite the square root of 2 as 2 to the 1/2 power. So we have the log base 3 of the first factor, which is 2 to the half. Right? That's the square root of 2. And I'll use the power property because again, this is just a personal preference. I don't like having radicals or fraction powers inside logarithms. Just a personal preference on my end. Plus, remember the product rule involves sums of logs. The log of the second factor, right? There's only 2 factors in here. The log base 3 of x squared. Right? And then each of these I can use the power property on, right? Each of these have a power, right? The entire expression raised to a single power. So I can apply the power property and say this first logarithm is equal to half, right? 1/2 times the log base 3 of 2, right? And 2 is not a nice power of 3. It's a power of 3, it's just not a nice one. Not a whole number or an integer or a fraction. So I'm just going to leave this log base 3 of 2 the way it is. Plus, and then applying the power property to this log, pulling the 2 out, where we have 2 times the log base 3 of just x now. Right? And because that's just x in the log there, x must be a positive number in order for this to actually work out. All right, and I leave it to you to test. Replace x with any positive number in these expressions and you'll see the original one and the final one have the same value all the time. Great. All right, the next example, 19, pardon me, we're still asked to expand the logarithm. So first, I look inside this log and there's not a single power, right? There's multiple powers, so I can't use the power rule. There is a product, but there's also, I see this fraction. This is a fraction, right? I see that this is a fraction. One numerator, one denominator, single fraction. A quotient, right? So I can apply the quotient property. So this would be the log base 3 of the numerator of this fraction, x times y squared, minus, right? Remember with the quotient property, it ends up being the difference of logs, minus the log base 3 of the denominator of this fraction, z squared. Alright, then I keep going, right? Keep looking inside the logarithms. This log here has a product inside, right? X times y squared. And this log has a power, right? Everything's raised to the second power, right? A single power inside. Alright, so I'm going to apply the product rule, the product property to this first log. Alright, so this first logarithm would be the log base 3 of x plus the log base 3 of y squared. Alright, that's applying the product rule to that first logarithm. Then we have minus, and then the log base 3 of z squared, I'm applying the power property. Pull that 2 out front, so we have minus 2 times the log base 3 of z. All right, we're almost done. Right, again, you look inside, you keep using the properties until you can't use them anymore. X is not a product, it's not a fraction, it's not a power. That's interesting. But y squared is a power, right? Everything in there is raised to the second power. So I can use the power property on this second logarithm, and then the last one has just z inside, so I'm done with that. So finally, this is equal to the log base 3 of just x plus, and then the log base 3 of y squared. I apply the power property to pull the 2 out front. That'd be 2 times the log base 3 of just y. Right. And then we still have this third term here, minus 2 times the log base 3 of z. Right. And now I can't use any of those properties anymore. Right, so this is it. And because you have x and y and z all inside these logarithms, all three of those, x, y, and z, must all be positive numbers in order for this to actually work. And I leave it to you to check. Right? Replace x, y, and z with any positive numbers you wish in the original expression and this final expression, and you will see that they end up giving you the same result, the same value. But I leave that to you to check, to test it out. Okay, number 20. Same deal. When I see a square root or a radical, I'm going to rewrite it as a power. Right? Just again, a personal preference here. And they're going to have you do it too, I believe, in this text. Yeah, so I look inside. We're still asked to expand, right? So I keep using these properties till I can't use them anymore. I see this is a single fraction, one numerator, one denominator. So I'm going to use that quotient property first. Right? So we have the log base 4 of the numerator, which I'm going to rewrite as x to the 1/2 power. Right? That's the same thing as the square root of x, the numerator. Minus, right? Minus the log of the denominator, right? Log base 4 of 16 y to the 4th. Okay, great. This log has a power in it, right? Something to a single power. So I can apply the power property to that. This logarithm has not a power, 16 is not raised to the 4th power. Yes, there's a single power in here, but 16 is not raised to the 4th power, right? The entire expression needs to be raised to a single power in order for you to be able to use the power property. So, but I do see a product in here, right? This is definitely a product. Okay, so applying the power property to the first log, we get 1/2 coming out. So this is 1/2 times the log base 4 of just x. And you gotta be careful with subtraction. Alright, I didn't do it with the log in the first one, number 19. But you're subtracting this logarithm. So you're going to be subtracting everything this logarithm is equal to. So if there's a minus sign, right, you got to worry about that. We're going to put this in brackets or parentheses, right? We're subtracting everything this log is equal to, which is the log base 4 of 16, right, the first product factor, plus, I'm using the product property, plus the log base 4 of the second factor, y to the fourth. But put this in brackets or parentheses, right? You're subtracting all of that. Right? And really, I should have put parentheses around this. Usually when you replace something with something equivalent to it, you put parentheses or brackets around it. But very often it's not needed. But here it is needed because I'm going to need to distribute now this minus sign. Right? We'll distribute the minus, subtract everything that log is equal to. I hope that makes sense. All right, and then there's only one other property I need using. Right, y to the this last log here has a power in it. Right, everything raised to the fourth power, a single power. And this log base 4 of 16 I can simplify. Remember, 16 is 4 squared, 4 to the second. So that's 2. Right. So we have finally 1/2 times the log base 4 of just x. Then distributing the negative here, we have minus the log base 4 of 16 we said was 2. Right. That's 2. And then minus a positive, so minus again, and then pulling the power out, we have 4 times the log base 4 of y. Right. But be careful with your subtraction, with your minus signs and stuff. Alright, and there we go. That's as simple as that gets, as expanded as it can get. I can't use any properties anymore. And once again, I'm going to point out that x and y must be positive numbers in order for these to actually be true. All right, and you can test it out, and I leave it to you. Right, replace x and y with any positive numbers you want, and you'll see the value of this original expression will be the same as the value of the final one. Right. Okay. The next one, this is the last page where I'm asked to expand, and then we'll be asked to condense, right, going the other way. Alright, so once again I look inside this log and I see a fraction, single numerator, single denominator. So I'm going to use the quotient property. So this is the log base 2 of, now again, roots, radicals, I'm going to rewrite as powers, right? Fraction powers. That is, the radicand, 2x plus y squared, so the quantity 2x plus y squared to the 1/2 power. Right, that's the square root of 2x plus y squared. Minus the log of the denominator, right? The log base 2 of z squared. All right, and then each of these are a power. Right? Remember, everything in here is raised to the single power of a half. Right? So this is a power. And so is this, right? Z to the second, everything in there is raised to the second power. So I can apply the power property. So pull the half out. This is 1/2 times the log base 2 of, and then what's left over when I pull the half out is 2x plus y squared. Minus, and then here I'm pulling the power out, 2 times the log base 2 of z. And that's it. This is it. Because this expression in this log is a sum. A sum. 2x plus y squared. It's not a product. It's not a fraction. And it's not all raised to a single power. Yes, there is a power in here, but the entire expression is not raised to that power, so I can't use the power property. So I'm done. This is it. All right, and some restrictions on the variables here. Right? Z needs to be positive, clearly, because of this log of z. And 2x plus y squared needs to be positive as well. Now another way of saying this, x needs to be greater than negative 1/2 y squared. Right? But here are the restrictions on the variables. So pick any positive number for z, and then really you can pick any number you wish for y and x, just so long as this happens. All right. So you could have y be a negative number. That's fine, right? Have y be -3, and then x can be any number greater than negative 9/2. So x could be -2 in that case. So, but these conditions have to be met, though, for whatever values you pick. All right. So as long as these conditions are met, the value of the original expression should be the same as the value of this expression I have in the box. But yeah, a sum you can't do anything with, right? There was no sum property. I mean, there was a sum in the product property. Right? There's a sum on the right side of the product property, but it's not the log of a sum. Right? There's no property where there's a sum inside the log, and you can do anything with that. Just be careful. All right, so this one here. Now, as I've said before plenty of times, I'm going to be rewriting all the radicals as powers. So this log base 2 of this big fourth root, see, everything is inside the fourth root. So I could rewrite this way. The radicand, which is 5x cubed divided by, and then 2y squared z to the fourth, right? All of this, the fourth root of all that. So this is all raised to the 1/4 power. All right. So I didn't use any properties. I didn't use any properties of logs yet. I just rewrote the fourth root as the 1/4 power. But you see in here, this is a power. I can apply the power rule, the power property, because everything in here is raised to the 1/4 power. So I will do that. I apply the power property, pull the 1/4 out, so we have 1/4 times, and then the log base 2 of, and then the radicand, right? What's left over when I pull the 1/4 out, you have 5x cubed over 2y squared z to the fourth. All right, and then again, like with the subtraction problem in number 20, if you look back at example 20, we're going to have to do some brackets here, some parentheses, because this is 1/4 times everything this log is equal to. So I'm going to need to put brackets or parentheses. We're going to be distributing the 1/4 eventually. And I see the log of a fraction here, right? The log of a fraction. So I'm going to rewrite that using the quotient property. So it's 1/4 times, and then everything this log is equal to. 1/4 times the quantity, the bracket. We have the log base 2 of the numerator, right? 5x cubed, minus the log base 2 of the denominator, 2y squared z to the fourth. Right. Now I'm going to keep these in brackets for now, because I want to start rewriting this chunk too. All right, so in this log, we have a product. Same thing over here. There's a product of 3 factors, 2 times y squared times z to the fourth, but there is a product in that log. And just like in example 20, we have subtraction in front of this. So remember, I'm subtracting everything this log is equal to. So I'm going to have another set of brackets. I'm going to have brackets within brackets here. So this is going to look a little complicated looking, but bear with me. So this is 1/4 times, and then brackets, parentheses, whatever you want to use. Right? Then we have this log base 2 of 5x cubed. I'm going to use the product property. We have the log base 2 of 5 plus the log base 2 of x cubed. Right? That's the product property applied to this first logarithm. All right, and again, there's no need for parentheses around that because it's not being multiplied by anything or subtracted, right? But I need parentheses or brackets around the next one. Right? We have minus, minus, and then you're subtracting everything this log is equal to. So I'll put a set of parentheses instead, or another bracket. And the log base 2 of this product is, the log base 2 of 2 plus the log base 2 of y squared plus the log base 2 of z to the 4th, right, using that product property. Close the parentheses on that, right? You're subtracting all this, right, all that log. And then I'm going to close the brackets as well, right, for the entire expression that 1/4 is multiplied by. All right, a lot of stuff. All right, so the log base 2 of 2 is 1. And we're going to distribute this subtraction here. Right? So first I'll distribute this minus to these three terms. Right? And we get the following. I'll bring up a new sheet of paper here, sorry. So we still have, 1/4 times bracket. Right? We have the log base 2 of 5 plus the log. Now I'm going to use the power property here and here and here, right? So we have, I'm going to write that here. We have a power, right here, x to the third inside that log. Here we have y to the second inside that log, and here we have z to the 4th, right? So I can use the power property also. So this log base 2 of x cubed becomes 3 times the log base 2 of x. And now I'm distributing the negative. Minus 1 minus and then 2 times the log base 2 of y, right, applying the power property. And then minus 4 times the log base 2 of z. And close the brackets, right? The parentheses aren't needed anymore because I actually subtracted each of those terms. Distributed the negative. And now I'll distribute the 1/4 to every single one of these, all 5 of these terms. So we have here 1/4 times the log base 2 of 5 plus 3/4 times the log base 2 of x minus 1/4, and then minus 1/2, right, minus 2/4 minus 1/2 times the log base 2 of y, and then minus 1, right, 4/4 minus 1 times the log base 2 of z, or just minus the log base 2 of z. And there we go. Totally simplified, right? No parentheses, no brackets anymore. And all like terms are combined and everything. Yeah, yikes. That was a big one. All right, now x, y, and z are all these arguments of these logs here. So x, y, and z must be positive numbers in order for this to work out. And go ahead and check it out. Now this might be a little harder to check because there's more terms to enter, but replace x, y, and z with any positive numbers, and the value of the original expression with this 4th root should be equal to the value of this final crazy expression here with these 5 terms. And I leave it to you to test that out. Right? Replace x, y, and z with any positive numbers, and it should work. Ooh, all right. So that was a pain, but still, just got to be careful. Right? When you're subtracting a log you're subtracting everything that log is equal to. You know, when you're multiplying a number by a log, you're multiplying by that number by everything that log is equal to. Right? So you got to use parentheses and brackets sometimes. All right. Now the final exercises, the final 7, I believe, we are asked to condense logarithms, which, as I mentioned on the properties page, is going right to left. So we're going to take multiple logs or multiple factored expressions and write them as a single logarithm. Right? So I'll write the steps out that I want to follow. Right? So this one will actually have some steps. You know, I'm not just going to be using the properties willy-nilly. So first, I use the power property from where needed. Remember that was if you see a number multiplied by a logarithm, put that number inside as the power of the argument. Right, so I'm going to do that first. Right? If I see any numbers multiplied by logarithms, and I'll say ignore negative signs too, right? But we'll get to that. Right, then, from left to right, taking two terms at a time. Right, from left to right, use the product and quotient properties as necessary. So use the product and or quotient properties as necessary, as needed. All right. So if you see, a sum of two logs, if you see the sum of two logs with the same base, turn it into a single log of the product of those arguments, right? Just multiply the arguments to get the new argument. Or if you see a difference of two logs, right? And I know I had these written out earlier, but if you see the difference, a subtraction with two logs of the same base, just make a single log, and the new argument will be the ratio or the quotient of these arguments, but it's got to be in a specific order. First argument's the numerator, the second argument is the denominator. All right, so number 23, again, we're asked to condense and simplify if necessary. All right, so here we have the log base 6 of 4 plus the log base 6 of 9. Now, none of these logs have a number in front other than 1. So I don't need to use the power property. But I do see a sum of two logs with the same base. So I can apply the product property. Right? I can apply the product property. So the log base 6 of 4 plus the log base 6 of 9 will be equal to the log base 6 of 4 times 9, which is the log base 6 of 36, and this is an easy one because 36 is a nice power of 6. All right, 36 is 6 to the second, so this is 2. Right. And if you want to check this with a calculator, I leave it to you, right, to check this with a calculator. Okay, great. 24, same thing. We're asked to condense, right, write as a single logarithm, get it down to be just one log. We have the log base 2 of 80 minus the log base 2 of 5. Now there are no numbers other than 1 in front of these logs multiplied by these logs, right? So I'm not going to use the power property. And now I'm noticing, right, that this is the difference, right, subtraction, the difference of two logs with the same base. So I'm using the quotient property here, right? So this will be equivalent to the log base 2 of a fraction. And the numerator of that fraction will be 80, and the denominator of that fraction will be 5. And then we simplify, right? This is great and everything, but 80 divided by 5 is 16. Right? 80 divided by 5 is 16. So this is the log base 2 of 16. And again, we have a nice result. 16 is a nice power of 2. 16 is 2 to the 4th power. So this is 4. Right. And there you go. And again, I leave it to you to check with a calculator or something, right? If you punch this in a calculator, you'll get 4 back, I promise you. Great. Alright, next. Alright, so here we have the log base 3 of 4 plus the log base 3 of x plus 1. Notice there's no numbers other than 1 in front of these logs multiplied by these logs, so I'm not going to use the power rule again. And then once again, I'm seeing the sum of two logs with the same base, so I'm going to be applying the product rule. So this would be equivalent to the log base 3 of 4 times the quantity x plus 1, right? The first argument times the second argument. And we can distribute the 4 here, and this is the log base 3 of 4x plus 4. Right. And that's it. Right. That's it. Now, because there are variables here, I would like to put, what restrictions we have on the variables. X plus 1, right, needs to be a positive number. Remember, you can only take logs of positive numbers to get real number outputs. So that means that x must be greater than negative 1. So there's the restriction. And the same thing would happen for 4x plus 4. If 4x plus 4 has to be greater than 0, you still get x is greater than negative 1. And I'll leave it to you to test this out. Right, replace x with any number greater than negative 1. So negative 0.5, 0, 1, a million, right? Replace x with any number greater than negative 1, and the value of this original expression should be the same as the value of this final one. But I leave it to you, of course, to test that out. Okay, next. Log base 7 of 3 plus the log base 7 of x minus the log base 7 of y. Notice there's 1 in front of that log, 1 in front of that log, and 1. Ignoring the negative sign, there's a 1 in front of that log. So again, I'm not going to use the power property. Now, next step is to go from left to right. You take 2 terms at a time. Right? You can only really take 2 terms at a time, and apply the product rule or quotient property as needed. So the first 2 terms from left to right is the sum, right, plus sum of 2 logs with the same base. So I'm going to be applying the product property. So this will be equal to the log base 7 of, and then the input of this log is, the product of these two, 3 times x, or just 3x. And then we still have this third term that we haven't used yet, so I got minus the log base 7 of y. And again, 2 terms at a time. Right now I have these 2 terms. And it's a difference of 2 logs with the same base. So I will be applying the quotient property. So this is equal to the log base 7, right, a single log of, and then the argument of this log is, the first argument, 3x, divided by the second argument, y. And there we go. That is condensed, right? The expression we were given that had 3 logarithms is now expressed as a single logarithm. And again, there are variables, so I would like to point out that x and y have to be positive here. Right? X and y both have to be positive numbers in order for this to actually be a true statement. And I leave it to you to test it out. Replace x and y with any positive numbers you want, and the value of the original expression should be the same as the value of the final expression. Wonderful. All right, keeping going with this, condensing logarithms. All right, now number 27. Now you see. I have some numbers multiplied by logarithms that aren't 1. Pardon me. You see 4 times this log plus 6 times this log. So in each of these, I can apply the power property. Power property on that log, and I can apply the power property to this log. Now that's just putting the number inside as the power on that argument. So this is equal to the log base 2 of, and then this input here, x to the 4th power, plus, and then the same thing for this next term, the log base 2 of y to the 6th power. So I apply the power property first, and that should be your first step in reversing these and condensing these. And then I go left to right, taking 2 terms at a time, which, there are only 2 terms here, 2 logs, and apply the, product property or quotient property as needed. This is the sum of 2 logs, so 2 logs with the same base. So I can apply the product property here. Say this is equivalent to the log base 2, a single log of, and then the product of these 2 arguments, right? X to the 4th times y to the 6th. And there we go. That is totally condensed, right? It's a single logarithm now. And once again, because you had x in there, y in there, y in those logs, x and y must be positive numbers in order for this to actually be true. All right. And test it out. Replace x and y with any positive numbers you wish, and the value of the original expression should be the same as the value of this final expression. And I leave it to you to test that out. All right, just got a few more. All right, here there is a number, right? Again, ignore the negative sign. The negative sign will be used when we use the quotient property and stuff. But there is a number other than 1 that's multiplied by this logarithm here, right? I have 2 times this log. So I can apply that power rule first. Right? So we have the log base 3 of x squared minus 1 minus, and then putting the 2 inside as the power of this argument. This would be the log base 3 of the entire thing to the 2nd power. So all of it, x minus 1 in parentheses to the 2nd power, right? The quantity x minus 1 squared. All right, so now that I've applied the power rules, now I go left to right and apply the quotient property or product property as needed. Right, and here we go. There are only 2 terms, and it's a difference of logs with the same base, so I'm using that quotient property. Right, we're applying the quotient property. So this would be equal to the log base 3. Right, 2 logs become 1, and the new argument is just the ratio of these 2, the quotient. So the numerator is x squared minus 1, and the denominator is this quantity x minus 1 squared. And this is great and everything, but this fraction can be simplified. Remember, x squared minus 1 divided by, x minus 1 squared, this can be simplified. So let's do that. The numerator factors to x minus 1 times x plus 1, right? Difference of squares, factors to a product of conjugates. And then you have the quantity x minus 1 squared in the denominator. And do you see that the numerator and denominator share a common factor of x minus 1? Right? One of those would cancel. So I'd be left with x plus 1 over x minus 1 when it's totally simplified. So this is equal to the log base 3 of x plus 1 divided by x minus 1. And there we go. That is as simple as it gets, and it's as condensed as it gets as well, right? A single logarithm. All right, now on top of this, x needs to be greater than 1 in order for any of this to work. Because if x were less than 1 or equal to 1, this log would be bad, right, in the original expression. X minus 1 has to be positive, meaning x has to be greater than 1. Right. Great. So pick a number, any number at all, that's greater than 1. So like 1.5, 2, 5, 10, 5,000, whatever, square root of 2. Plug it into the original expression and the final expression, right, and they should be the same value. No matter what number you pick, that's greater than 1 though, right? It's got to be a number greater than 1 for this to work out. Wonderful. Alright, now last page here, last two. Again, we're asked to condense. So notice this log in number 29, this logarithmic expression. I'm going to be using that power property on all three terms, right? There's 4 times a log, minus, and then 2 times a log, right? A number times a log, power property again. Minus, and again, we're going to ignore the minus signs for now. And then minus 3 times a log, another power property. Right. So putting all those powers in, we get the log base 10, right, log of x to the 4th power, minus, and then putting the 2 inside, we have the log base 10 of y squared, minus, and then putting the 3 inside, the log base 10 of z to the 3rd power. Alright. And then we go again left. Now we're done with the power rules, right? Then we go left to right, 2 terms at a time. Only 2 terms at a time. And apply the quotient rule or product rule as needed. Well, these first 2 terms, that's a difference of logs with the same base. So I'm applying the quotient property. Right, so this is equal to the log, 2 logs become 1 log. And the new input is the fraction of the old ones, the quotient, x to the 4th divided by y squared. Alright, and then you still have this third term that we haven't touched, right? So you got minus the log of z squared. And then one more time here, we have a difference of 2 logs. So again, I'm applying the quotient property. Now this is going to look a little funky. I'm taking this over here. 2 logs become a single log. We have the log of the first input would be the numerator. So x to the 4th divided by y squared. Notice I'm putting it in parentheses. That's the numerator. Divided by, and then z squared in the denominator. Now this is a complex fraction. This is ugly. This is pretty ugly here. But we can pretty easily fix this. You should know how to simplify a complex fraction by now. I would just multiply the numerator and denominator by the LCD, which would be y squared. Just multiply the above the bar and below the bar, multiplying by y squared. And then we get the following. This would be the log of, and you see up top the y squared's canceling. You have x to the 4th in the numerator. And then below the bar, we have z squared y squared, or y squared z squared if you put them in alphabetical order like people usually do. There we go. And that's, the fraction's as simple as possible. It's not a complex fraction anymore. And the expression is as condensed as possible, right? It's a single logarithm. And then once again, based on the beginning here, x, y, and z need to be positive in order for any of this to be true. Right. Right. And check it out, right? Test it out for yourself. Replace x, y, and z with any positive numbers you wish, and the value of the original expression should be equivalent to the value of this final expression. Great. All right, and this is the last one. Thank goodness, right? We're an hour 45 minutes here. Probably should have broken this up, but oh well. Again, I got some power rules to use, right? There's 1/3 times a log, right? So I'm using the power property here. Minus, again, ignore the minuses for now, and then we got this 3 times a log. I'm going to use the power property here. Right. So applying the power property, putting the 1/3 in, we get the log base 10 of x to the 1/3 power, which you can write that as the cube root of x if you wish, which I'll do in a little bit here. Minus, and then putting the 3 inside, we have the log of, now remember, that becomes the power of the entire expression inside. So the entire quantity, x plus 1 to the 3rd power. Right. And then left to right, 2 terms at a time, apply the quotient rule and product rule as needed. This would be another quotient rule one, right, because it's a difference of 2 logs. So this becomes a single log, right, the log of, and then the numerator would be x to the 1/3 power divided by, and then the denominator is the quantity x plus 1 to the 3rd to the 3 power, right? And this is great. All right, this is totally acceptable because this fraction doesn't simplify any further, and I can leave it at that. Now, of course, you could rewrite these things. Log of x to the 1/3 power is the cube root of x divided by the quantity x plus 1 cubed. This is equally valid. All right, this is equally valid. And if you'd like, you could expand, take x plus 1 to the 3rd. Say it's the log base 10 of the cube root of x, divided by, and then x plus 1 times x plus 1 times x plus 1 again, right, taking those 2 at a time, would be x cubed plus 3x squared plus 3x plus 1 in the denominator. So I mean, this is also equally valid, but I'd be totally fine with the first box. And it's a single log. It's as condensed as it can get, and the fractions simplified. X to the 1/3 and x plus 1 cubed don't have any common factors, so that's good. And of course, x needs to be positive, right? You have x needs to be greater than 0 here. X needs to be greater than -1 here, but -1/2 or something wouldn't work for this first log. So you do the intersection of those. X needs to be positive again. X needs to be a positive number in order for what I said here to be true. And again, test it out. Replace x with any positive number, and the value of the original expression should be the same as the value of the final expression. And I leave it to you to test that. Wonderful, wonderful. All right, so the key takeaway from all this, right, is these properties, right? I'll put the property page up. Here's those 7 properties I wrote out throughout this video. Get them in your head, all right, memorize them. I definitely recommend memorizing them. They make things a lot faster for you. And yeah, I hope that watching me go through these, 30 different examples, 30 questions, helps you in some way when you're asked to rewrite logarithmic expressions using the properties of logs on your own. And thank you very much for watching.